And we're recording. Okay, so welcome to the Advanced Math Circle. So let me go ahead and get the screen share going here. And then I will say some things. Okay, so last time, the topic that we were going over, we didn't actually finish everything. So that's going to be the goal for today, is to finish this off and then start the next topic. So very rapidly, in case there's any of you here who weren't here last week, just so that you're up to the same page, I'm just going to very quickly give you the words and the definitions of things that we're going to need. So just really quick. Last time we looked at consecutive numbers. So consecutive numbers, and let me go ahead and get my pen to be working. Very good. So consecutive numbers, remember, these are just back-to-back numbers. So like 7, 8, 9, and so on. Those are consecutive. So that's what that word means, is numbers in order. We had consecutive odd integers and consecutive even integers. So that's just numbers back-to-back that are even or odd. So some consecutive evens would be 2, 4, 6, and 8, right? And again, this is just a reminder of the terminology we had before. Some consecutive odds would be 7, 9, 11. And we also talked about you could have negatives. You could have like -3, -1, 1, and so on. And notice I'm always putting these in increasing order. Okay, we saw that we can always write even numbers like this as 2 times n. So for example, if you have the list of even numbers 2, 4, 6, and 8, notice that this is 2 times 1. Notice that this is 2 times 2, 2 times 3, 2 times 4, and so on. And all even numbers can be written that way. We also saw that we can write odd numbers very similarly. We can write odd numbers as 2n or 2k plus 1, right? Or minus 1. If you take this list here and just add 1 to it, right? 2, 4, 6, 8 becomes 3, 5, 7, 9. And this is 2 times 1 plus 1, 2 times 2 plus 1 for 5, and so on and so forth. So when we are trying to write an even number in general, we'll write 2n, and when we're trying to write an odd number in general, we will write 2n plus 1. Okay, again, this is all stuff we saw before, how to write odd numbers. Just gave you that formula. 3 consecutive numbers. We saw that you could write them with letters. So for example, I could do n plus 1, and n plus 2, and there were many ways to do this, but this would just be 3 consecutive numbers in general. So we saw that last time. Okay. If there's any quick questions, please ask, but again, this is just terminology from before. We saw how to write consecutive even numbers. So for example, 2, 4, and 8 were consecutive evens. So in general, an even number would be 2n. The next even number would be 2n plus 2. And then the next even number after that would be 2n plus 4, right? We don't do 2n plus 1 because, for example, in the case of 2 and 4, 2n plus 1 would be an odd number. That would be, say, 3 in this case, and that is not a consecutive even number, okay? 2, 4, 6, yes, someone messaged me to correct me. Yes, the next even number would be 2, 4, and then 6, okay? Because remember, they're consecutive, so we don't skip anything. Consecutive odd numbers was the same idea. If a general odd number is 2n plus 1, let's say 1 if n was 0, then the next one would be 2n plus 3, right? And the next odd number would be 3. So this would be 0 plus 3, and so on and so forth. So 2n plus 5 for the next one. And there are multiple ways to write these, but in general, this was a way to write consecutive odd numbers. We looked at combining like terms. So here, 2n plus 2n gives us 4n. And we would add the 1 and the 3, if that's what that is. My screen's a little cut off on the top there. And so 1 and 3 would be 4. And we could pull out the 4. We could factor this and write it as 4 times n plus 1. So simplifying means to combine like terms. Factoring means to pull out common multiples. Okay. We'll see more of this in the examples we do. This is just a really quick reminder of examples we did. And we ended on this problem. Is this where we ended? I think so. Of the sum of 4 consecutive natural numbers, can it ever be divisible by 4? And the answer was no, because if I write down 4 consecutive numbers, well, I could do n plus 1, n plus 2, and n plus 3. And then if I add them all, if I take their sum, right, I can rearrange this. So this would be n plus n plus n plus n for 4n, and then 1 plus 2 plus 3 for 6. And this wasn't divisible by 4. 4 can't be divided into this because 6 is not divisible by 4. If you tried to write this out as being divided by 4, then you would get 4n over 4 plus 6 over 4. The 4's cancel, but 6 over 4 is a fraction. It can reduce to 3/2, but it's a decimal number. It's about 1.5. So you cannot have the sum of 4 consecutive natural numbers be divisible by 4. Okay. So again, that was just a reminder of what we had done last time. We're now going to keep going. Are there any really quick questions before we get into what we're going to do today? Okay. And again, if any of that was a little fuzzy, we're going to see some of it again in the examples we do. So we'll get more practice today. All right. So let's take a minute to look at this. We have a list of what if I have an even number plus an even number? Is that going to be even or odd? And then we ask ourselves, what if I add an even and an odd? What if I add 2 odds? What if I multiply 2 evens? What if I multiply an even number and an odd number? And what if I multiply 2 odd numbers? So let's take just a moment. Everyone think about this for a second, and we'll call on one of you to fill this out. Just give you a minute or so to think about this. Okay. Okay. So let's see. Anisha, would you be willing to share what you got?
Yeah, sure. So for the first one, I got even.
Okay.
And then for the second one, I got odd.
Okay.
And then the third one, I got even.
Cool beans.
And then I got even again.
Mhm.
And then even. And then odd.
Very good. Okay. So you don't have to do for every one of them, just for any of them. Can you share how you got this? What was your thought process?
Usually I just pick a random even and odd number. I usually do 1 and 2 because they're really small.
Okay.
And just add or multiply them.
And then just saw what happened. Okay, good. So just to elaborate a little bit, for example, to see that even plus even was even, let me do this. You did 2 plus 2, which is 4, and I'm just going to keep using 1 and 2. So if we use example numbers, right? If we use 1 and 2, for even and odd, 1 plus 2, that's an, I should write it the other way around. For even plus odd, right? That gave us odd. For odd plus odd, that gave us even. For even times even, we got even, and so on and so forth. So 2 times 1, we got 2, which is still even, and then 1 times 1 is 1, which is still an odd number. So this was a good way to check to see what it is. What you do want to do, oh, very good. Omkar, would you like to share what you actually just typed for even plus even?
Well, when you add 2 even numbers, you're adding a 2n plus 2n, which results in 4n, which means 4n is always be even because it's divisible by 2.
Okay, so very good. There's one little thing that I'll point out here you have to be very careful about, though. If you do 2n plus 2n, where you use the same n,
Yeah, it's n is
cool.
different. So you
There
could
we
do
go.
like 2n plus 2m.
There you go.
And
Nice.
then
Yes.
you'd have, but then you'd be able to factor out the 2 from 2n plus 2m to get
Perfect.
2 times n plus m.
Yes. Okay. So what you just did was, instead of just picking some numbers, right, you did it with the formulas. So no matter what even number you pick, what you actually just proved is that if I add two even numbers, I always get 2 times a natural number, right? You could just call this k if you want to see that it's 2 times a natural number. And so you've proven it, right? And so that's avoiding the issue of, if you pick specific numbers, maybe you got lucky with what you picked. In this case, like everything here is true, but in general, you would use the formulas. Very good. So just to show the next one, if you used formulas for even and odd, you would do 2n plus, let's keep the same letters, 2m plus 1, right? Because this is an even number plus an odd number. But when you do that, the same thing you just said, you could factor out a 2. You'd have 2 times n plus m plus 1. You would have 2 times an integer, excuse me, plus 1, which is the definition of an odd number. So I'm not going to do that for every single one, but in general, for each one of these, that's what you would do if you wanted to prove that it was true, right? Is you would write down the general formulas. Okay. Give me 1 sec right here. Are there any questions on this? Make sense? Okay. All right. So very good. So let's get into the heart of, so why did we want to do all of these things today? Well, there's a problem coming up. Now, this is a definition, but what we're going to be getting into is an interesting problem to solve using all of this stuff that we've built up. Now, just as a reminder, prime numbers are numbers that can only be divided by 1 and themselves, right? So some examples of primes would be 2, actually, 3, 5, 7, 11, 13, and so on and so forth, right? I'm sure a lot of you have memorized a lot of these. But the reason these are prime is that the only number that cleanly divides is themselves and 1. There's nothing else that goes in. So just as a reminder, that's the definition of a prime number. So let's look at this problem. We want to find all positive, so no negative numbers here. And positive also means that 0 doesn't count, right? 0 is neither positive nor negative. So we don't want to include 0 in this. So when we say all positive integers, we're talking about 1, 2, 3, 4, and so on. So we want to find any and all of them for which all 3 of these numbers are prime, all at the same time. So that's the question, right? Take a moment to think. Does anyone have any ideas for how we can even start to answer this question, right? Because this one's a bit of a step up from the stuff we saw before. So take a moment to think. Anyone wants to share an idea? And it's okay if you don't come up with an idea, that's fine, but think about it. How would you begin? Okay, so I've already got some ideas. Let me wait a little bit longer, give people a second to give everyone else a second to think.
You can also message us individually for me and Connor if you have answers and questions.
Yes, thank you. I forgot to mention that. Remember that Connor and Maria are both my assistants. And so aside from messaging me, you can message them directly as well with your answers. And we'll take turns calling on people. Okay. Okay, so I'm going to go ahead and this means that next up, either Connor or Maria will call on someone because I've called twice. But Michael Ligori, sorry if I butcher your name, would you be willing to share your idea?
Sure. I made a hypothesis that if we added all of them together, maybe that'd be easier because then we'd be able to tackle them all at once.
Okay.
So maybe if they're all added together,
Mhm.
we could find all of them at once. I don't know.
Okay, yeah, it's something to start with. So if I add these all together, what do I get? What do they add up to?
(12n minus 12).
Good. So we've got 3n plus 4n plus 5n. 3 plus 4 plus 5, that's 12n. And then these are all minus, but it's really the same thing, right? 4, 5, and 3. So minus 12. So we added them together. We got this. But of course, the thing is, remember, we want to try to make some observations about what's going on here. So either you, Michael, or someone else, can anyone comment on what they would do with this or what they can notice about this?
It's divisible by 12, so which factors out to n minus 1.
Okay, cool, cool. Yes, thank you, Amal. So we have 12 times n minus 1. So this number is divisible by 12. That's cool, right? So let's note this. So this is divisible by 12. Okay. So that's true. Now, does anyone have any idea for why that's helpful? Remember, we're trying to think, we're trying to find n for which all three of these numbers are prime, right? So can anyone, again, let's take a moment, right? This isn't necessarily an easy question, but why is it helpful to notice that this is divisible by 12? Take a moment to think. And Maria, if you get what you deem an interesting answer, feel free to just call on them whenever.
I'm still waiting for answers.
Okay,
Have-
remember, it's not just me, guys. Remember, message Maria too. Okay, I've got one. Some of them I'll share when they're general. Someone said it helps narrow down our answers. This is true, but in what way? And if you have an answer, wait just a second for the person who said that. So it's true, it gives us a restriction, but we want to know what the specific restriction is. Okay, so Joshua, can you elaborate on how it helps narrow down our answers by chance? Oh, you just typed it, but would you like to share?
Do you hear me?
Yes.
Well, I most likely am wrong, but what I said was that it helps us narrow down our answers to have only numbers subtracted by 1 to be divided by 12 after giving us our prime number.
Oh, I see. So that's not wrong, but what you said was because it's basically the same thing as this, right? Just you said it more fancy, and that's fine. You articulated that very well, but yeah, we know that the sum of these has to be a number subtracted by 1, which is divisible by 12. Yeah, that's what this says. But we want to think of how this relates to where, let me go back to this actually, right? For some reason, I wanted to bring y'all's attention to this, right? I wanted to point this out. So somehow this is relevant, right? That's kind of a meta reasoning, right? I'm not just showing you random things. We've got a bunch of tools and we want to try to put them all together. So let me try, okay, a little bit of a spoiler there, but let me try to coax this out. The number 12, just anyone, just unmute yourself and answer. Is this number even or odd?
Even.
It's even.
It's even.
It is even. Okay. So now, question. Based on that, could all three of these guys be odd numbers? Is that possible? Take a moment to think. Yeah, not too long. We'll just wait like 30 seconds.
Can I say something?
Wait just 30 seconds and then sure.
Okay.
Approximately. And is that who I think? Okay. Okay. Okay, I said 30 seconds. So go ahead.
So if you look at 3n minus 4, you're multiplying an odd number by n and then subtracting an even number, which means that if you were to have n as an even number, that would mean that 3n is also even, and subtracting 4, which is also an even number, would give you an even number which isn't prime. Unless it's 2.
Ooh, but hold on. So you just said if it's an even number, it can't be prime. Is that
Unless
right?
it's 2.
Ah,
Because unless it's 2, then it can't be prime if it's even, because then it's divisible by 2. And
okay.
then also 5n minus 3, you're multiplying n by an odd number and then subtracting an odd number. So if n is also odd, then you end up with 5n is odd, and then subtracting 3 makes it even and thus not prime. So 3n
Unless
minus
it's 2.
4 invalidates any even values of n, and 5n minus 3 invalidates odd numbers of n.
Mhm.
So no value of n works.
Unless one of them is 2. Right? So everything you said, that's good reasoning, right? You just have to be really careful about one of them could be 2. 2 is a prime number, right? And then the other one would be odd, and that's okay. You are floating around where we're going. So hang tight. Your mind might be blown pretty soon. So similar to what you were saying, let's not focus on the specifics of whether these become even or odd because of how we're multiplying, adding, or subtracting, right? Not because that's an incorrect approach, just because there's 3 numbers here, and that's kind of a lot to keep track of. So instead, let's think of the fact that when we added them all up, we got an even number, right? We got 12 times something. So if I've added these all up and they're even, could they all be odd numbers, right? If they were all odd numbers, we'd have odd plus odd plus odd. What would that be if they were all odd numbers? Would that be even or odd? Anyone? It would be odd. But what do we already know?
It adds up to 12 times n minus 1, which is an even number times a random number. Even.
And an even number, let's go back to the chart, right? An even number times a random number, right? If I have even times even, I get even. And if I have even times odd, it's still even, right? So we know that when we add these all up, the answer comes out to be even. Because of that, they can't all be odd, right? If they're all odd, then they all add up to an odd number, and we already know that doesn't happen. We already know that's true. Does that make sense to everyone? Okay, or does it not make sense to anyone? Would be the thing that would cause someone to unmute themselves and ask something. Okay, in particular, notice the reasoning, right? Notice the way that we're asking, instead of trying to answer the really complicated question head on, we're breaking up the hard question into much easier questions that are building towards the answer, right? So we've got they can't all be odd. Well, if they can't be all odd, right, then either one of them is even. We don't know which one, but let's just write it in any order because they can't all be odd. Or maybe 2 of them are even. Okay. So maybe all 3 are even. Let's just humor all 3 of these possibilities. Okay. So let's label these possibilities. Let's call this is possibility A, possibility B, possibility C. And here's what I'd like you guys to do.
Even plus odd isn't really a possibility because that's also odd.
Correct. Okay, so you jumped the gun because that's what I want people to think about. But good, yes. For B, so we'll scratch this one. For B, even plus even would be an even number. This would be even. And then even plus odd would still be odd. And we already know that's impossible, right? The exact same, we know it can't add up to an odd number, okay? if we look at, so if we look at part A, we've got even plus odd plus odd. What do I get when I add two odd numbers together? Anyone?
Even.
Any number.
Even. And then an even number plus an even number would be even. On the bottom, they're all even, right? If I have a whole bunch of even numbers and I add them all up, what am I going to get?
Even.
Even. Yeah, because you'd have even plus even. So as far as knowing that our number has to be even, it looks like either option A or C could work. Now, don't unmute yourself. Give everyone a minute to think. One of these is not possible. I'll just tell that to you. One of these is not possible. Take a minute to think and try to figure out whether it's A or C that's not possible, and tell me why. Okay, so take a minute to think. Remember, you can message Maria as well with your answer. Show the initial problem again. Yes, so just as a reminder, the question we are trying to solve is we want to find all positive integers for which all three of these are prime numbers. Okay, so keep that in mind. All three of them have to be prime numbers. Very good, yeah. Oh, I spoke out loud. Someone sent, Maria, did you get any responses?
Not to this one, no.
Okay, oh, guys, remember she exists.
I guess you're more popular than I am.
Yeah. So Omkar, would you like to share what you just said?
Yeah, so even plus even, while also having all three be prime numbers, would mean that it's 2 plus 2 plus 2.
Right.
And if that's also 3n minus 4, 4n minus 5, etc., then they can't all be the same number.
Very good. Yeah, these are all clearly different numbers, right? You can check that. So this isn't possible because the only way that could happen is if you had the same prime number, 2, over and over and over again. So in actuality, option C is impossible. The only possibility we have is one of them could be even, which means it's 2, and the other two could be odd, right? That's all we have so far. Okay. Oh, okay, I've jumped the gun. I forgot I had a slide for everything that we were just saying. So yeah, when we add those three numbers together, we get 12 times n minus 1, which means it's an even number. And we've just established that there can be one even number and two odds, not necessarily in this order. I'm not saying the first one has to be even, but one of them could be even and then the other two must be odd. That's what we figured out so far. Okay, so we've now figured out that one has to be even and two, yes, one has to be even and two of them have to be odd. Some of you have already done this before we went through the general reasoning, but using that, can we figure out what value of n causes these guys to be prime? Now, comment on this. You can guess, right? Because some of you have. So in the real world, a lot of people do guess. You have something, you just throw numbers in, you see what works. But what's going to be way more interesting, even if you've guessed and you've figured out what the value of n is, what's going to be way more interesting is if you can give me a process, if you can give me some steps you're doing that for similar questions, maybe if we were asking a slightly different question, you could do the same steps and get the answer. So if you already figured out what n is, that's awesome, and I'll have you share it in a minute, but see if you can give me like a process. Okay. And as a hint, we know one of them has to be an even number. Okay. Now this goes back to, I forget who it was. Maybe it was Joshua, but someone was talking about when you're multiplying these and adding and subtracting, whether n was even or odd, right? Someone was talking about that reasoning. Use that here and ask yourself which one of these could actually be even. We know one of them's even. Which one of these could possibly be even? Take a minute to think and let everyone else think before you answer. Okay. Okay. Alternatively, if you find it difficult to think about which ones are even, ask yourself, are any of these odd all the time? And the key thing is all the time, right? We don't want it to flip-flop for different values of n. We want to check for any n that I plug in, are one of these always odd or always even? Okay. Maria, how's your inbox looking?
I have one student, Nisha.
Go ahead. Anisha?
Oh, yeah, sorry. So I got 2 because I got that 3n minus 4 is the number which has to be even.
Okay.
So, which means it has to equal 2. So I just did 3n minus 4 equals 2, and then I solved for n, and I got 2.
I see. Okay, so you did 3n minus 4 equals 2.
Yes.
Okay. All right. Cool beans. Okay, and that's the only even prime number. That's why I did that. Very good. Now, you said this one has to be even. Can you give me a reason why neither of these other ones can be even?
Well, that's because they all subtract by a odd number. So it depends what the first number is. It could get to an even number or an odd number.
Okay, cool. So you're right. It could be either even or odd, but you've established that 3n minus 4. Well, you say this has to be even. Not necessarily. Look, if I plug in 3 here, if I did 3 times 3, that would be 9 minus 4, which would be 5, right?
Yes.
So you're right. This could be even. Remember, the question, we want to find out all possible answers. So that's why we're going through all of the cases. So this will work, and we'll flesh that out. But we want to make sure that one of these can't be even. And then Maria, you're saying Michael has something to add? Go for it.
Michael, if you want to share.
We only hear static for some reason.
You're gonna have to check your mic.
I picked 1 because you can because if you plug in 1 in that last expression, that will equal 2, which is the only even prime number.
Okay.
And then the other ones, the other 2 will both equal to -1, which is technically a prime number. By definition, -1, the only way you can get it is by multiplying 1 and -1.
Okay. So let me check the wording on the question right quick. Positive integer. Well, okay, but that's n. Okay. So you're right. Technically, by the definition I gave you, -1's prime. We are okay. English would be nice if I could speak it. The historical precedent is that we usually just don't consider negative numbers as prime. You're right that technically by the definition I gave you, it counts, but we don't normally consider them as prime. Okay. But, okay, so you just tried n equals 1. You saw that this was 2, and these ones fed backwards. Okay, so all good thinking here. Give me 1 second. Let me remember how to get an eraser on here. Okay. So
Actually, by that definition of a prime number, I think if you were to consider any negative numbers prime, I think -1 would be the only one you could consider prime, because for all the other negative numbers, -1 is a factor.
yeah, very good. And so it would actually break the definition of everything else. For example, 2 would no longer be prime because 2 is divisible by itself and 1 and -2. So if you allow for negative numbers, there aren't really any prime numbers anymore. That's why we don't do it. Very good point that I had forgot about. Okay, so let me kind of lead you guys towards something here. So, see if I can get the pen. Okay, so right here, 3n minus 4 could be an even number, and the only even prime is 2. So this one could be equal to 2. Kind of in a reverse reasoning to what Michael just shared, this one could be an even number. And again, the only even prime is 2. So these two right here would give possible answers. Now, more importantly, I'm asserting that 4n minus 5 can't be even. That's kind of what I just said, because I said these two are even, and I like skipped over this guy. Can someone tell me why that one right there, 4n minus 5, why can that never be an even number? What's up with that?
4n is always even because you're multiplying n by an even number.
Mhm.
And then subtracting 5, which is an odd number, will always give you an odd number.
Very good. This is always even minus odd, and so it will always be odd. Make sense? Does it not make sense to anyone? Okay. So the only two possibilities, as far as if one of them's even, is either this guy is the only even prime, i.e. 2, or this guy is the only even prime, which is 2. And then I solve them. So this is what Anish actually said, was solve this. So we add 4 over. This gives us 6. And we divide both sides by 3. And so we get 2. Similarly, for this one, we'd add 3 to both sides and divide by 5. Who wants to tell me what we get if we solve this one for n? If we add 3 and divide by 5, what do we get?
And you would
1.
Yes. Very good. So I add 3, I get 5n is equal to 5. Dividing both sides by 5, I get n equals 1. So the two possibilities for n are 1. Those are the two possibilities, and then we check them, right? When if we plug in 2, well, I'll leave it to you guys. So some of you plug in 2 to this formula and tell me what 3 prime numbers you get. And someone else plug in, well, actually, we already did 1, right? Because we were just told. So when we plugged in 1, we got -1, -1, and 2, but we just had the conversation that we don't consider negatives as prime because it breaks all the prime numbers.
for 2, I got 2, 3, and 7.
Very good. And notice those are all prime numbers.
Would 0 be considered as prime?
No, because 0, there's several ways to think of this. Here's what I think makes the most sense. 0 is divisible by everyone. Give me a random number. Just someone spit out a number.
0 is divisible by everything except
9,742.
9,000, I lost some of it, 142, let's say. 0 divided by that is 0. So other than 0, 0 is divisible by everyone. So he's the most not prime you could possibly be. And I heard I think they were saying that it's not divisible by 0, or whoever it was who was talking. Go ahead.
Yeah, I said 0 is divisible by everything except itself.
Correct. Right. So if you say it that way, it's even more not prime, right? Any other questions or comments from anyone? Okay. How do y'all feel about this question? Notice the reasoning, right? It was less about, because, if you just had tried to, there we go. But the key is, if you go back to the question, the key is all. So the reason, because you may be feeling, hey, I figured out that n equals 2 works. So why would I do any of the rest of this if I guessed n equals 2? Well, because you would then have told me that 2 works, but you wouldn't really be able to convince me that it's the only thing that works, right? Maybe there's a whole bunch of other numbers, 32,445,000,000,003 or something, that also just happen to work, right? So we want this reasoning, we want this way of breaking down the problem to show not just that here is an answer, but here is the answer, and there are no others. If you understand this reasoning, then you've also understood that the only answer is actually n equals 2. Okay. All right. So let's do some more. Let's do some more math. Let's do some more questions. Okay. So here's the next one. Let me try to clear up my screen just a bit. Perfect. That's exactly what I need. I just figured out a thing that makes my screen bigger. Perfect. Okay. So now we want to find 20 consecutive composite numbers. Composite, the way we're going to think of that is not prime. Okay. Ooh, I'm being cut off. I'll do it down here. Composite means, oh, it's already here, not prime. So if I'm not a prime number, by definition, I'm composite. Okay. Again, talking about whole numbers, not going to talk about decimals or fractions or anything. And remember, consecutive just means numbers in a row. So we want to find 20 consecutive composite numbers. Okay. That's what we're going to try to do. So here's something that might help. Take a moment to stare at this. Don't immediately unmute yourself. Let's give everyone a chance to think for a second. See in this how many consecutive composite numbers you can find. So how many numbers can you go in a row without hitting primes, with sticking with composite numbers? Take a moment to see how far you can go. And in particular, while you're doing this, look for any patterns. Okay, so if someone just commented on a pattern they see. Let's go ahead and jump in. So 1 second.
I have a few answers if you want me to jump in any point.
Oh yeah, go ahead. So you first, the students who messaged you first.
So Tanvi, do you want to go ahead and share what you got? I hope I'm saying your names right. Correct me if I don't.
I said there were 5 from 32 to 36.
5 from 32. So okay, so yeah, so we've got 32 all the way up to 36 composite numbers. Okay. Okay, okay. Does anyone see a longer pattern or just any other patterns that they want to comment on or anything?
There's another sequence of 5 from 24 to 28.
Okay, 24, 25. Very good. Yep, yep. So there's a sequence of 5 composite numbers. Okay, I'll use a box to mean prime. So in other words, these are prime numbers. Very good. So let's just go ahead and let me actually, I changed my mind about the box. Let's just not mark the primes at all. Okay, so just going through really quick, if we circle all the composite numbers, that is all the numbers that are not prime, we see that we have all of these guys. Okay, and then 20, 22. So
Doesn't
note that
21 also?
very good. Yes, because that is 3 times 7, right? Sneaky prime, sneaky not primes, especially when I'm going fast. So if I miss a composite, please let me know.
39 is not a composite.
That is
Never mind,
true. That is true.
Isn't it 13 times?
Not true. It's 13 times 3.
Oh, yes. My bad. I'm too trusting. Yes, that's correct. That's 13 times.
Sorry.
No, you're good. That's 40, 42, 44. This guy. 49 is 7 squared, 50, 48. All right. I have no problem admitting that I don't remember all of them. 47 is this guy. Does anyone want to tell me if that guy's prime or composite?
Pretty sure it's prime.
Okay.
Prime.
Yeah. And then one's in this weird state of do we count that as a prime or not? But I'm just ignore him for now. So we've got this. Notice how it's kind of erratic, right? We had a sequence with only one number in it, one number. This one was 3 long, and then we had 1 again, and then 3 in a row, and then 1 again, and then 3 in a row, and then all of a sudden there's one that's 5 long, right? And then 1, and then 5, and then 3, and then 1, and then 3, and then 3. So it's kind of erratic, right? How long it seems to go before you get composite numbers. So that's a little interesting. Okay, I had some stuff here breaking it down, find 3 consecutives and so on, but we've gone through this, right? Okay, it looks like we're considering 1 as a prime. So we've seen how far you can go. Come on, turn the page. We tried the brute force method, right? And we're talking about what can you observe, and that was where I was pointing out. Let me just use my mouse at this point, where I was pointing out that we have this erratic pattern, right? Of sometimes there's just 1 all by itself, right? Goes back and forth. So that's just to give you kind of a feel for this pattern, right? For this pattern of how far can you go by having composite numbers. So let's take a little step. We're going to come back to that idea of finding composite numbers, consecutive composite numbers all in a sequence. We're going to come back to that. But we're going to need some tools in order to do that. Has everyone here heard of factorials before? Or a better way to say this, has anyone not seen factorials before, actually? Just let us know. Okay. Okay, so I hope silence means you've seen them before. I'm still going to go in a little bit of what they are. Okay.
Haven't heard anything yet, but I assume so too.
Okay. So just very briefly, if you've never heard of them before, they have a very simple definition, right? So it's right here. The definition's right here, an example is right here. If you give me a number and you do factorial, you simply multiply them all the way down. Okay, so 5 factorial is 5 times 4 times 3 times 2 times 1. Now, given that, what I would like you guys to do, and we'll take a moment for you all to try this, is I would like you guys to factor this number. And if you're wondering, what do you mean factor? Well, remember, for example, just a bit ago when we had 12n minus 12, we were able to factor that because we could pull out 12 and write it as n minus 1. And so what I'm asking you to do is do something like this to 4 factorial plus 3 factorial, right? And try to not put too much effort in, right? Don't actually compute what that number is. Don't actually do 4 times 3 times 2 times 1, right? See what that is, and then add another number in factor tree. Too much work, way too much work. Try to do something simpler, more like this. So give everyone a minute to see how they would do that. Okay, so Omkar, would you be willing to share what you got?
Yes, I got it's 4 factorial plus 3 factorial is equal to 5 times 3 factorial. You can obtain that by equating 4 factorial is equal to 4 times 3 factorial.
Okay.
And then, so you have 4 times 3 factorial plus 3 factorial. You can factor out the 3 factorial to get 3 factorial times 4 plus 1 or 5.
Very good. Okay. So let me write this down. And let me put in an extra step, in fact. So he's factoring out the 3 factorial. And again, just because this throws people sometimes, you can think of this as 1 times 3 factorial. And because I wrote it in this way, I'm going to pull out the 3 factorial to the other side, in fact. So we have 4 plus 1 times 3 factorial. And he was saying that's 5, and he's correct. And I could write 5 times 3 factorial. I could write 3 factorial times 5. So the main idea here.
Y plus 1, though.
Y plus 1? Oh, well, notice the 4 times 3 factorial plus 1 times 3 factorial. Right? So it's if I...
You just do 3 factorial.
Yes, but there would still be a 1 right here.
Well,
so,
yeah.
Okay, yeah. The 1 being written here was just to, if anyone was going to be confused by that, you can put that there, but you don't have to. As long as you understand that there would be a plus 1 here, you're fine.
Hey.
Okay, cool beans. So the main thing we want to notice is that if we're adding 2 factorials, then there's going to be a greatest common factor we can pull out, right? And so we want to see if there's some way we can use this to help us find lists of composite numbers, okay? Well, let's practice just a little bit more. What if I've got a factorial plus something that isn't a factorial? So take a minute, factor this as well, doing something similar to before. So take just a minute to see how you would do that. Not coffee. Okay. Let's see. Okay. Maria, have you gotten any responses?
A few. Do you want me to call on somebody?
Absolutely.
Or do you want to give it another minute for a couple more people?
Go ahead and call on someone there.
Raphael, do you want to share or no? I know you wrote something for last time. I don't know if you want to share for this time.
Oh, yeah, that was for last time.
Mm-hmm.
Yeah, so for this time I got 2 factorial, parenthesis 3 factorial plus 2.
Okay, so let me write that down. Now, you know what I'm going to ask you, right? Can you walk me through how you got that?
Oh, yeah. Well, I just saw that both of them to be divisible by 2.
Okay.
So I just factored the 2 out.
Ah, but be careful. This isn't just 6.
6 factorial isn't 2 factorial times 3 factorial.
Correct. Right. What is the definition of 6 factorial? If I wanted to write it all out, what would it be?
6 plus 5 plus 4 plus 3 plus 2 plus 1.
Basically, except not plus.
Times. Sorry.
Yes, you're good. So let's just write that out and stare at it. Okay. Plus 4. So let's look at that. Let's look at it written that way. What does it look like you can factor out when I write it like that?
Oh, you can factor out the 4.
Correct. And what's going to be left behind when I do that?
A 1 for the 4, and then
Yes. And what else?
a 3 fact.
You see it, right?
Yeah.
Those guys.
Yeah.
So that's what you were missing before, but does that make sense?
Yeah.
Okay, so that's what you have to be careful about with factorials, right? It wasn't just 6 divided by 2. It was actually, you have not just 6, you've actually got a 2 totally separate from the 6 in here. And so what's left behind is just everything that wasn't 4. So 6, 5, 3, 2, and 1. If you really wanted to, excuse me, 1, not 6. Ba-ba-ba. Okay. And notice this is a bit awkward, right? If you tried to write this with factorial, the best you could do is 6 times 5, and then you'd have 3 factorial right here. Or if you wanted to write it even differently, you could say this was 30 times 3 factorial. But that's the best you can do, right? There's not really much of a cleaner way that you can write this.
Or 31, couldn't you?
31. No, because this isn't, you would need this to be 6 times 5 times 3 factorial plus 1 times 3 factorial so that they would be like terms, right? But you don't have a 3 factorial back here. So they're not like terms, right? Be just like if you had 6 times 5 times x plus 1, right? You couldn't add these guys because they're not like terms. Does that make sense?
Yeah.
Okay. Cool beans. All right. Okay, so good warm up. Take a minute to think about this. Can you use these ideas to come up with, and this isn't an easy question necessarily, right? But using this notion of factorial, can you come up with 20 consecutive composite numbers? So just to kind of set your brain for a second, notice that when we went all the way up to 50, right? The longest we found was a sequence of 5. And I'm asking you to give me 20 of them in a row. So probably just going out further is not going, you might be here a while. So instead, we might want to try to be a little sneakier, right? We want to be a little bit more clever and try to use this idea of factorial, right? Think about what you notice when you're adding a factorial in another number. When you're adding two factorials, what can you notice about them? Okay. Just take a minute to think about that. I can give you hints.
I got one student so far, but everybody send your answers.
Just a little bit longer. Is the student's answer like the answer for 20 consecutive composite numbers, or is it just an idea? Because I'd like to give a hint.
Just an answer. So are you looking for ideas at the moment?
For the moment, yeah. So if they've got a full answer, hold for just a second. In fact, let me go ahead, right? If you've only gotten one response, let me kind of point something out to people right quick. So just have a look at this. Have a looky here. Notice if we do, say, 5 factorial and then 5 factorial plus 1. This is just as an example, right? I'm not going for 20 consecutive composites. That's way too big. But let's just kind of take a look at what's happening when I do this. Right? 5 factorial is 120. It's 5 times 4 times 3 times 2 times 1. If I add 1, I get 121. If I add 2, I get 122. If I add 3, I get 123. If I add 4, I get 124, right? And so notice this is a sequence of 5 composite numbers, right? Okay. And I got that from starting with a factorial and going up. Now, is that a coincidence, right? Is there something I have to be careful with? What have you, right? But here's like a small example of kind of a way of thinking you might want to consider, right? When I start with 5 factorial, I was able to use that to get 5 consecutive composite numbers. Okay, but keep factoring in with factorials in mind, right? Be careful. But there's an idea. Okay. Okay. So I haven't gotten any messages. Maria, have you gotten any other responses yet?
I have one student who's thinking about it. I don't know if that student wants to share or do you want to just go into it?
Well, if they want to share, go for it.
Hi, Michael. We're having issues hearing your mic.
I kind of have an idea on what the method is. I think that maybe the factorial that we're using is either it might be like 5 factorial or 7 factorial, because I noticed when we had the grid up, all composite numbers were either factors of 2, 3, 5, or 7, which happen to all be prime 1 through 10. So I think that's one of the factorials.
Okay,
so it might be.
Yeah, you're good. I'll just unpack what you were. So you were saying that all the composites here had one of these prime numbers that went into it, right?
Yes.
Okay, because for a minute I was like, well, 22 has 11, but you're not saying it only had those. You're saying it had one of them. So that's actually because we only went up to 50, right? If I kept going, for example, you want a composite number that's not divisible by any of those, whatever 11 times 13 is, right? So it's not true that all composite numbers are divisible by one of those guys, right?
I kind of have an answer. Well, not an answer, but more of an idea.
Just more
So,
stuff? Yeah. Hit me.
In the example you showed of 5 factorial, 120, 121, 120, all the way to 124, you said you got 5 composites, right? So shouldn't the same be true of 20? So it should start off with 20 factorial and then work its way up.
And then work its way up. Okay, so this was the type of thing I was trying to hint at, right? And you'd keep going. However,
oh wait, the 1 doesn't work, I think.
Yeah. So, okay, so here when I did 5 factorial, I happened to get a composite when I went to the +1, right?
Yeah, because 20 is even, so you wouldn't get the thing with 20, so 20
Well,
factorial plus 1.
So more so, it's that we want to be sure that it works. 20 factorial is really big. 20 times 19 times 18 times 17. That's very, very, very big. That's a huge number. So it's hard for us to check. But more so, we want to be really sure that whatever we do actually works and we're not just lucky. So when I did 5 factorial and I went to 5 factorial plus 1, the number I got was composite. It was 11 times 11. But for small numbers, consider 2 factorial plus 1, 3 factorial plus 1, 4 factorial plus 1. Do all of these give you composites?
Only the 4 factorial, that's 65. I mean, 25.
You're faster than me. Yes. So this one gives you 3, which is prime. This one gives you 7. So actually, there's an issue with doing the 5 factorial and the 5 factorial plus 1, right? What's the solution? How do I fix it?
You could ignore it and then start off with 20 factorial plus 2 and then work all the way up to 21.
Cool. So right here, if I kept going with my 5 to get a list of 5 composites, I could have done 5 factorial plus 5 and then 5 factorial plus 6, right?
Yeah.
Okay. Here's the thing. This is the right idea. Other than by staring at this number, though, how do you know for sure that this, let's suppose you don't know this is 126. Can you argue to me why 5 factorial plus 6 is a composite number? Can you tell me why that must be true without just looking and seeing that it's 126?
5 factorial is going to be even, so 6 is even as well. So it's going to be divisible by 2.
So let's write that out explicitly. Let me do it down here. If you look at 5 factorial plus 6, by the way, who is talking right now? Because I can't tell.
Amal.
Amal? Okay, cool beans. Yeah. Cool beans. So notice if you write out the 5 factorial as 5 times 4 times 3 times 2 times 1, you can write out the 6 as 3 times 2 times 1. And what have you got?
3 factorial and in common. So you take out 3 factorial.
So we want to be sure that what we're writing down, there are always a common factor, because if so, we will have a composite number.
Yeah.
Does that make sense?
Yeah.
Okay. Does there anyone for who it doesn't make sense? Does anyone have questions on that, on this idea? Okay, so let me write down that idea. We want 20 consecutive composite numbers. So we'll start off with 20 factorial plus 2. We're not doing 0 and 1 because we saw just on the previous page that when we do the plus 1, it doesn't necessarily always give you a composite. It could be a prime number, right? But if we do 20 factorial plus 2 and 20 factorial plus 3, all the way up until 20 factorial plus 20, right? And then 20 factorial plus 21, right? And I could even go further, actually, 20 factorial plus 22, right? And I'll stop there. The reason we know these are composite is that 21 is 3 times 7, and 3 and 7 are both factors of 20, factorial, right? if you write it out, it's 20 times 19 times 18, right? Let me actually do that. The rest of these, you can see very clearly these are composite because these numbers are smaller than 20, right? 20, you could factor that out. So this would be 2 times something, right? This would be 3 times, because 3's in here, something. When you get down here, you could pull out 20 and you'd have 19 factorial plus 1. Here, for these last two, the reason it works is 20 factorial is 20 times 19 times 8 times 7 times 6, 5, 4, 3, 2, and 1. 21 is 3 times 7. And notice, doesn't matter what you pull out, you could pull out a 3 from everything. And then you would have 3 times some number, right? And so it would be composite. You could pull out 7 if you wanted. You could pull out both 3 and 7 if you wanted, right? I'll just suppose I pulled out 3, and then I would have 3 times some number. And for 22, 22 is 2 times 11, right? So if you had all of this plus 22, same logic, there's a 2 in here, there's an 11 over here. You could pull either one or both of those out, and you would have, let's say, 22 times some number. And so that gives you a composite number. So in general, if you want to have a list of n consecutive composite numbers, a trick to do this is to just do n factorial plus 2 all the way up until n factorial plus n plus 1. Plus 2, actually. You could go further, because as we did on the other page. Any questions on this from anyone? How do you guys feel about factorials, about this idea, using them to make really long sequences of composite numbers?
Well, would n be able to be 1 if you wanted one composite number?
So that's a good point.
That wouldn't work, would it?
So what would it mean for n to be 1? You would want to construct one consecutive composite number. So for then, if we use this formula, so let me turn the page and do what you're saying. So let's say I wanted one consecutive composite number. Oh, it's the end over. Then if I use the formula, my formula is, okay, give me a second for my pen to work. Keep. Oh, 1 second. Technical difficulties. Okay, come over here. Screen share, go back. Thank you. Okay, and give me my pen. Okay, so if I wanted to do one consecutive composite number, notice my formula is n factorial plus 2, and then we keep going, right? So if n equals 1, what would that give me? That would give me 1 factorial plus 2. That would give me 3, which is not composite. So you're right. For n equals 1, it doesn't work. All right, what if I wanted 2 consecutive composite numbers? So if n equals 2, then that would be 2 factorial plus 2, which would be 4. That's composite. And I can see immediately if I go to the next one, it starts breaking down. So I'll leave this as an exercise, right? This works for big numbers, right? This idea for big N, right? N20 or larger numbers, right? It seems to work. We just saw that for n equals 1 and n equals 2, it kind of breaks down. For you to do at home, think about, when does it start working for sure? Check n equals 3, check n equals 4. These are small numbers. You can do it, right? See when it starts working, and then see if you can see why that is and what's going on there. So for big numbers, this reasoning works. For 1 and 2, we have problems. Okay, so as far as factorial and composite, that was what we had. Now I would like to let's see, what time is it? We're good. So I would like to introduce you guys to exponents, kind of in preparation for next time. So just before I jump into that, are there any other questions on anything we did right here?
I have a different answer to the
this one?
Yeah, to the 20 composite numbers.
Go ahead.
I think
Me-
that all you have to do is multiply all prime numbers less than 20, and then you can make the sequence be that number, and then that number plus 1, plus 2, plus 3, up to plus 19 to
So
get.
instead of using just 20 factorial, you just took the first 20 primes.
Yes.
Okay, so let's
Oh,
look
no,
at
not the first 20 primes. All the first primes that are less than 20.
the first primes that are okay. So let's think about that, because I didn't think about that. Let's see. So the first primes that are less than 20. So you want to take these guys and multiply them all together, you say?
Yeah, and then to start with that number equals n, and then the sequence is n plus 1, n plus 2, up to n plus 19.
So I have a question for you. How do you know for sure that when you do plus 1 plus 2, you don't get a prime? And the reason I ask is, for example, if I do 2 times 3, right? If I keep it small and I get 6, right? That would be just doing the first couple of prime numbers, right? Suppose I wanted a sequence of length 5. So I would take all of the prime numbers less than 5, right? That's like the idea. So if I did that, the first one's composite, but what's the next one? What does this give me if I do that?
That gives you prime number 7.
Uh-huh. So that is a good idea, but you should check what's going on there, right? Because it doesn't work for small numbers. So is there some big number where it does start working or not? And why not? The reason we did this factorial approach is because we were able to show explicitly that it does work, right? Because I can go through step by step and I can say 2 is a factor of this, 3 is a factor of this. That was the key, that I know everything I'm writing down here can be factored out with this factorial. But when you take all the prime numbers and multiply them to, well, all the prime numbers up to a certain point and multiply them together, you do not have this guarantee that you can always factor out everything you're adding afterwards. Does that make sense?
I was thinking that for numbers other than 1, if for numbers other than 1, then the number should always share a factor with the original n, if n is the product of the prime numbers.
Check it. Yeah, so give that, assuming you'll be here next week, go ahead and check it, and like afterwards, I'll be very curious. I'm not saying that's wrong. That might be true. I don't know. See if you can prove it, right? Because that's where the money really is in math. If you can prove it using letters, then you win. So that might be true. I just don't know.
So I think in order to eliminate the issue of plus 1, you could start the sequence at n plus 2 instead. I don't
like
know.
you did for factorials. Yeah, that might fix it. If there's anything to be fixed there, depending how big you go. This is good. But
You just need to, yeah, if you multiply all prime numbers up to 19 and then start with n plus 2, I think you might be able to create a sequence.
perhaps.
And you might actually have to multiply that by another prime number because you're starting with n plus 2 instead of n. I'm not sure though.
Yeah. I'm not sure either. Saying I'm not sure doesn't mean, no, that's just, if you become a mathematician, you will spend most of your time not being sure and then spending a lot of time finding out. So because I know it would take a lot of time to find out, you should look into that. And I probably will too if I can't sleep, because that's a good one. But I'm going to keep going for now. We have finished this. That is a cool idea. You should try it. See if there's other ways to come up with lists of composites. I want to ask everyone though, in preparation for next time, does everyone here know what the power rule is? Or rather, does anyone here not know what the power rule is? Like when I say power rule, what comes to mind?
Like, do you mean like exponent rules, like exponential rules?
Very good. Yes, that is what I mean.
Oh.
So let me try to clear my screen here. Hold on. I'm a complete noob at PowerPoint. Well, let me go ahead because it's going to be on the next one. So as a preview for what we're doing next time. Okay, we're not going to go deep into this. Just want to give you an idea of if you want to sort of prepare in advance for anything as far as what's coming up. Do this. Okay. So just as a very brief example, if we were talking about power rules, right? This is the first thing. I skipped past the title card because regardless of what the general thing is, anyone, just go ahead and unmute yourselves because we're just doing this real quick, just as like a warm up for next time. Can anyone tell me what 2 cubed means and what the answer is?
So 2 cubed means 2 times 2 times 2, and it
Cool.
would be 8.
And it would be what?
8.
Very good. Someone else? 2 to the 4.
It's 2 times 2 times 2 times 2, which is 16.
Very nice. Okay. Someone else? What's 2 cubed 2 to the 4th like this? How would you do this?
Be 2 to the 12th.
Not quite. I know what you did.
2 to the 7th, I think.
There we go. Okay. So you actually jumped ahead to shortcut. So what this explicitly would be 2 by 2 by 2, right? And then 2 by 2 by 2 by 2, right? Which would be 8 times 16, which would be, Maria, you tell me in a second. I'll write it down, whatever that is. And so the shortcut, if you count the number of 2's here, there's 7 of them, right? So the shortcut is that this is equal to 2 to the 7th. So for
128.
128, thank you. Oh, I used to be a computer science major. That's embarrassing. Okay, so this type of thing, power rules, right? Exponent rules is what we're going to be using next time for the topic that we're going to be covering. So kind of inspired, let me see what was on my, yeah, we'll do these two. Before we do that, inspired by the mental switch that just happened where someone said that this was actually 12, when it would have been 12 is if we had had 2 to the 3rd to the 4th. So I've already said what this would be. This would be 2 to the 12. But can someone tell me why that's what it is?
You're multiplying 2 to the 3rd 4 times, so that's 3 times 4.
Excellent. Yeah, so 2 cubed times 2 cubed times 2 cubed times 2 cubed. The painful way to do that is write out 2, 2, 2, 2, 2, 2. There'd be 12 of them. But if I just use this shortcut again, I could just group, right? That would be 2 to the 3 plus 3, so 2 to the 6th. And then again, 2 to the 3 plus 3, 2 to the 6th. And then I use the shortcut again, 2 to the 12th. So just being very comfortable with rules like this. Okay. Again, there's no shame in this, right? There's all kinds of things I don't know. And what I've learned very quickly is that I just need to say when I don't know. So is there anyone for which this is new? Is there anyone who doesn't know this? Please let us know. You can even type in the chat if you're embarrassed. We won't say who it is, but we just want to know going forward if everyone's comfortable with this.
And it's okay to admit if you get confused between 3 times 4 or as if you're just, in our other example, 2 to the power 3 times 2 to the power 4. Mm-hmm. Sometimes, it happens where you might confuse addition with subtraction. I mean, addition with multiplication. It's okay to admit that sometimes it trips you out.
If I don't make a bunch of arithmetical mistakes every day, then that means I didn't do enough math that day. Okay, so there's one person who I won't name, right? But one person did say that they didn't know it, but they think they understand. So that's even better, right? You don't know this, but you're understanding the idea and you follow. So let's just do one more of this warm up and then we'll stop here for today. Can anyone tell me how to write 1/2 using exponents? How would I write this down as a power?
2 to the -1.
Very good. Let me break that up into a couple steps, but yes, this is 1/2 to the 1. And you could think of this as instead of multiplying 1 by 2, I'm doing the opposite of multiplication, right? The opposite of multiplication is division. The opposite of having a power of +1 is having a power of -1. So this is just a notational thing by convention. Having negative powers actually means you're dividing. So with that said, can someone else tell me what 1 over 2 cubed would be written in exponential form?
2 to the negative
3.
Good. Yes. Very good. Yep. And that's just kind of the rule for how it works. So last thing, what is 2 cubed over 2 to the 4th?
It's 2 to the it would be 2 to the negative 4 over 2 to the no, sorry.
Is there a way you can simplify it?
Yeah. No, you're good though. Yeah. Go ahead.
It would be 2 to the 4th over 2. Wait, hold on. Sorry.
You're good. Yeah, yeah. The wording can be tricky with these, right?
Wouldn't you subtract them?
Yeah, so that's the shortcut. Yes. So
Which one do you subtract from?
yeah, what order?
Well, wouldn't it be like -1? 2 to the -1? No. Or
No, yes. Yes.
yeah, 2 to the -1.
So what order did you subtract those?
4 minus 3 from the denominator to the denominator.
So 4 minus 3, would that be -1 or +1?
Sorry, yeah. Denominator to the denominator. Sorry, yeah.
You're good. So the numerator minus the denominator. Yep. So numerator, oh, I'm getting cut off. Num minus denom. Yep. That's a shortcut though. Let me write it out in painful detail. So this would be, well, I guess it's not that much detail. This would be 2 cubed times, right? Just kind of use the same stuff from before. Oh, if it's a fraction, it's in the bottom, then it's really times to the negative power. So this would be times 2 to the -4. Use the rule where you add the exponents. This would be 2 to the 3rd plus -4, which would be 2 to the 3 minus 4. I'm writing way more steps than you have to. You should be able to write these steps, right? If someone was like, oh, I really don't get it, you should be able to write out all of these steps so that they can see it. And 3 minus 4 is -1. Now, this is a bit of a shortcut. Suppose you were trying to help someone, right? And they still tell you, yeah, I still don't really see why this is happening. Okay, how could you unpack it even further? Well, go even further back then, right? What did 2 cubed mean? It meant 2, 2, 2, right? And what did 2 to the 4th mean? 2, 2, 2, 2. Agreed? 2 times 2 times 2 times 2, right? And so at this level, I should switch colors, I guess. At this level, let's go magenta. You could just cancel, right? This cancels with that. This, you don't have to do it in order, but I will. This cancels with that. This cancels with that, right? So there's only a 1 left on top. And so pen color, red. And so this would be 1 over 2. Oh, hey, but we already decided what that was on this page, right? So we already know what that is. Don't even have to think about it. That's just, I already did that work. That's 2 to the -1. Okay. So this was just meant to like, okay, make sure you know these things. If you don't, practice them a bit. Okay, and then we'll get into more next time. We'll keep building, and then we will do interesting problems, right? Just like the previous set of slides I had. I'll go ahead and show the problem, but we're not going to do it today. Just like the previous slides I had, we had some pretty basic stuff, right? You add an even and an odd number, you get an odd number, you multiply them, you get an even number. We dug into all of that just so it was fresh, and then we could use all of it to do a much more interesting problem, like, can all 3 of these things be prime? And we used all of the stuff we saw before. So here, we need to make sure we're comfortable with exponent and power rules, right? This question is, again, not too hard. We'll do it next time. We'll break it down. If you don't know how to do it, don't feel discouraged. If I say something's not too hard and you're like, oh, geez, I don't know how to do it, that's fine. All I mean is there's harder and more interesting questions coming, which we'll dig into for fun, right? Remember, we're doing this for fun. There's no grade here. This is just, let's play around with numbers. Okay, and if you're curious, right, let me rearrange. I can show you how complex the problems will get. So we'll build up. I'm intentionally clicking past a lot of this. We'll build up with examples to answer a question like this. right? For today, we had, could these three things be prime at the same time? That was a fun question. We'll be looking at, 3 to the power n. Can I always write it as 3 consecutive integers being added together? So that might be something you want to think about, and we'll do it next time. We'll talk about what we've seen. We'll talk about, hey, could we add it as more than 3, maybe 7 consecutive integers, right? We'll keep playing around with 2 to the n. With 3 to the n, and then we'll do 2 to the n. And we'll try to figure out if we can write that as a sum of consecutive odd integers in particular. And you might wonder, why for 3 to the n did I talk about consecutive integers, but for 2 to the n, I'm talking about consecutive odd integers? Why did I need to put odd in there, right? So you might want to think about that. So again, we're not going to do these. We will next time. I'm just giving you a taste of what's coming, that this is kind of the pattern. You do relatively simple things, get really comfortable with them, so that the hard problems just become the simple problems in several steps. Okay. So if anyone has questions and wants to, so that's the end of the presentation. If everyone, for attendance purposes, would please write their name and by in the chat, that would be great. Give it 1 second. Please make sure not to send it privately. Send it to everyone in the group chat all at once. So if you send it privately, that's okay. Just like switch it to everyone. And if you have just general math questions, you're welcome to stick around, right? And chat for like 10 minutes or so. So in particular, I'll just do this one orally. Someone asked, can a number be to the power of a decimal? The short answer is yes. The easiest example I can give you is if you've ever heard of a square root, right? So the square root of 4 is 2. You can think of the square root as actually being 4 to the 1/2. And 1/2, that's a decimal number. That's 0.5, right? So the short answer is yes. And you've seen it before. Now, I imagine you mean much more weird decimal numbers, and the answer is yes. It just gets harder to calculate by hand.
Yeah.
Okay, cool. Yeah.
I think I can prove, I think I might be able to prove what I said earlier about the sequence of composite numbers.
Mm-hmm.
So
using primes, yeah.
Yeah, so what I was saying is if you want to generate a sequence of n composite numbers,
Mhm.
you can multiply all primes less than n plus 2. And multiply all primes that are less than n plus 2. And then every number you need to add to n to generate that sequence will always share a factor with one of those, one of the factors of that number will always be one of those primes. And since all of those primes are the factors of the number you start with, that means the number you start with will always share a factor with all of the numbers you end up adding to it to generate the sequence.
I believe you.
I think you said correctly.
That, and I agree. Yeah, like that sounds correct. If you're curious what an actual proof would look like, you would have to say, let n be a given number. And you would have to say, let P1, P2, like P with a subscript, like P sub 1, P sub 2, up to, let's say, P sub L, be all the prime numbers less than n. And then you'd have to write all of those multiplied together and start adding those numbers up and showing that you can always factor out some P sub I, right? So when you want to write it really carefully, it can get messy. But the idea that you're saying and why it's true, I'm pretty sure that is correct. And you could write it all very carefully using only letters and no numbers, and you could prove that. I believe that's correct.
Yeah, but depending on the number, you have to write all the primes, but you cannot get the general formula. The way we did can provide you the formula for, it doesn't have to be 20, right? No matter what number can be, that generate the formula. But in your case, your answer is correct, but you're using prime numbers, list of prime numbers. Those are not having any formula. So the answer itself doesn't have to be neat.
Yeah, so what Dr. Kwon is saying is the reason we liked factorial, again, she's not saying that you're wrong. She's saying that that's harder, and here's why. It probably feels easier, like mentally, it feels easier because you're more comfortable with prime numbers than factorials. But what Dr. Kwon is saying is if I ask you, hey, what is 319 factorial, for example? Well, I can tell you it's 319 times 318. There's a formula. But if I ask you, what is the 319th prime number? The reason the primes are so interesting is that there is no formula. The only way that you can tell me what the 319th prime number is you would have to list out the first 319 primes, and you'd have to go, that one, that the 319th number I wrote down after checking all of these, that's that prime number. But as far as just having a formula that you can work with, we don't have one for prime numbers. That's why.
I see what
Yes.
you're saying, but
Yeah, we
one
don't have one yet.
is
We don't
that you
know.
said the 319th prime, when really it's the prime, the largest prime less than 319, or less than or equal to 319.
Okay, but I can just make this bigger than, so it's the.
But yeah,
so that,
your point still holds. But
yeah, you're right. It would be, that's not too hard to find, but now I want the formula to work for 32 trillion or something. Yes, yes, understood. And as Maria said, we don't have a formula for prime numbers yet. Cynical skepticism reigns over here on my end, but yes, that's technically true.
Wait, we're free to go, right?
Yes.
Oh yeah.
This is just extra.
Okay,
Yep.
bye.
Ciao.
All right. Bye.
All right.
Did anyone else want to have a question or a share while you are on? Simon, do you have a question? Just checking in.
Go. Again, Atega? Do you have one? Nope. Okay.
All right, I'm taking Simon out.
Okay. Oh, and end recording.